Okay, Fluid Statics, Chapter 11. What is a fluid? Matter phases, that's important. Characteristics of solids, liquids, and gases. Definition of density, definition of pressure. Pascal's pressure, gauge pressure, absolute pressure. So, probably not going to do everything in this chapter, but I will point out the important stuff as we come to it. In matter, you have solids, liquids, and gas. And so solids have a structure. Fluids are close, but they tend to move around, and then gases, the atoms are separate. In terms of water, it takes energy to go from, well, any compound, but in terms of water, it takes energy to go from solid to liquid. So what you will see is when water changes from a solid to a liquid, its temperature will stay the same until all the solid is become liquid. Then temperature will go up, and the same thing will happen when it turns to gas. So when it's in solid, it's in like a crystal structure, and it's as close as they can get. Now, atoms in a solid, depending on their temperature, will vibrate. So you get vibrational. And then when it goes to liquid, you get rotational and vibrational, because they're able to move around each other. And then when you go to a gas, you get something called translational energy. Now, that's what I remember from chemistry, and it's always served me well. So liquids deform easily when they're stressed. They don't spring back to the original shape. They flow. The liquids placed in a container with no lid on it remains in the container. And gases tend to go all over the place. One of the good experiments is to heat, cool, and compress atoms and molecules and watch as they change between solid, liquid, and gas phases. So if you take ice and you heat it and you put a thermometer in where the ice is, you will see the temperature will stabilize once that ice starts melting, and then you will see the temperature stabilize when it boils. If you captured it, you would see the temperature then rise after it all boiled and became gas. Density is an important concept. Density is defined as mass per unit volume. So if you've got so much mass and so much volume, then density is that mass divided by that volume. And that's used quite a lot. And the symbol is the Greek P, and then here are some densities of various substances. Liquid has a density of 1, and this is times 10 to the third kilograms per cubic meter. So it'd be 1,000. Let's see, yeah, it'd be 1,000 kilograms per cubic meter. So if you've got a cubic meter of water, you got 1,000 kilograms of mass. That's about right. And it's 1 gram per milliliter. So yes. So you got densities of solid, densities of liquids, densities of gases. And you can see that they go down as the densities go down as the substances change states. So that's kind of neat. I can have a ton of feathers and a ton of bricks. Obviously the bricks are more dense, but since the fact that they're both a ton, they would balance. A good take-home experiment: sugar and salt. If you put a pile of salt on one end of a ruler and a pile of sugar on the other, and you made it to where they balanced, you would see which one had the greater density, because it would be the smallest amount. Pressure is force per unit area. Now this is one of the fundamental hydraulics formulas that you use. Actually, hydraulics and pneumatics. And it's Pascal's law. Why don't they say that? Pressure is force divided by area. So if you have a small amount of force on a small area, you don't feel it. But if you get a larger force on a small area, then you feel it. Pressure exerts at right angles to whatever is containing it. So what they're showing here is a tire, and they're showing the valve stem. And so pressure is always acting at a right angle to whatever is holding it. And if you go in the valve stem, you've got pressure that way. If you're swimming in the water, the pressure is operating at right angles to you. Okay. Pressure is mass times gravity times the area, or divided by the area. So you can find it from density. And what we notice in real life is the further down you go, the more pressure you get. That's the physical concept they want you to be aware of. So if I go down to the base of a dam in a lake, I'm going to have more pressure there than I will if I have than if I'm up near the surface of the dam. So they're going to derive this equation. So pressure is height times the density times gravity, which sort of looks like potential energy, which is mgh. Well, m is part of the density, h is the height, and there's the g. So my pressure at the bottom is going to be greater than the pressure at the top of a liquid. So here's a problem where they're actually using it on a dam. How much force is on unit area as you go down? So the force will increase per unit area because the pressure increases, and so you've got more force, and so you build the dams that way in order, because we got more force going against it. And then atmospheric pressure is the weight of the air above us on a square meter, and 1 atmosphere is 1.01 kilopascals. In the American side, it's 14.7 pounds per every square inch. So if I have a square inch down here and I want to do the American, I will have 14.7 pounds of air above that square inch all the way up into space. So that would be the weight. So that's the American. To go with the metric, so average density, Pascal's principle, there's Pascal. Okay, they finally got it. So change in pressure applied is transmitted to all. Now this is an interesting problem in a hydraulics. And this is how jacks work. When you jack up a car, you are putting a smaller force on a smaller area. And what's happening is you are creating a pressure. And that pressure is then going to a larger cylinder, i.e. the body picking up the car you're jacking up. And so that pressure, same pressure against a larger area, has to produce more force. So that's how you can jack up a car, so to speak. They're just, this is a more simplified version. They have a check valve, so as you build pressure in there and you go to lift the handle, it doesn't go back down. But then as you pump up this little side, the big side also pumps up, same pressure, and then that area is what lifts the car. So it's a physics principle using a jack. And we know the pressures are equal on both sides, the areas are different, so the forces are proportional. Force in the area are proportional. So if I use something 1 square inch and 1 square foot, which is 144 square inches, I get 144 times multiplication of my force. So that's what's happening, and they're working through that. Same thing applies when you apply the brakes in your car. Your pedal is applying a small force, but it is creating a pressure in all your brake lines, and that pressure going against the area of the cylinder pushing out the brake pads is what stops your car. So you don't have to push as hard as you need to physically stop the car. Same process. Gauge pressure, absolute pressure, and pressure management. Okay, gauge pressure is what a gauge reads. So most gauges will read 0 if they're out in the atmosphere or they're unhooked to things. And that's just because of the way the spring is set up to go to 0. But what we know is that gauge pressure, or anywhere on the earth, we have 14.7 psi of atmospheric pressure from the weight. Well, at sea level we have 14.7. The higher in elevation you go, it goes down a little bit, but it doesn't go down a great deal. So gauge pressure is what your gauge reads, and it's reference to it's not counting that the atmospheric pressure. Okay, so in absolute pressure we have to add back in the pressure due to the atmosphere. So on the English side, we take our gauge pressure and all we do is we add our atmospheric pressure, and then we get absolute pressure. So if your tire gauge reads 34 psi, the absolute pressure is then 48.7 psi in the tire. That's absolute. And absolute pressure, as well as absolute temperature, become important when you're dealing with gas laws. So area is area, but volume is volume. But when you start talking about pressure and temperature, you have to go to an absolute scale. And if you don't go to an absolute scale, then you're introducing a false 0. and it works out for both pressure and temperature. So it seems a little bit petty that we're talking about absolute pressure versus gauge pressure. Why would we ever use it? Well, we're going to use it eventually. Absolute pressure is the sum of gauge pressure and atmospheric pressure. So, so if your pressure gauge goes to 0, you know that that's a gauge pressure, or anything you read from a gauge is a gauge pressure. Your absolute pressure's at least 14 psi above that. Okay. The manometer is a way to measure atmospheric pressure, and I don't think I do a whole lot with that. One's open. If they're both open to atmosphere, it's even. But then if you close one side, then you can change the pressure, either increase it in a balloon or pull a vacuum when you're sealing peanuts. It's systolic, diastolic. I'm not going to get into the body pressures within the body. I'm gonna leave it outside the body. It's in the textbook if you'd like it. Conversion units for pressure, going from inches of water to PSI is a good conversion to sort of learn. And then inches of water can be millimeters of water, or meters, and then you can get to atmospheres or whatever you want. Archimedes principle, free body diagram. I don't think I use this either. Other than to realize that ships only float because they're displacing more weight of water than what they weigh. And I think this is also how they measure your body mass index, or your density as a person. I think we're done. Surface tension is a nice little topic to get into, just not in terms of solving any problems, but noticing that, you know, on the side of a glass the liquid tends to kind of crawl up, or if you read a beaker or a test tube, you will see a U-shaped level of the liquid, and you always read to the lowest because of the surface tension that's drawing it up on the side. And I think they're going to show that. Also explains how insects are able to walk on water because they're light enough, and there's enough tension on the water to hold up their light weight, whereas there's not enough tension to hold us up. Let's see, P1, P2. Surface tension of some liquids, it's something that's measurable. There's a chart. And yes, I would say pressures in the body we're not going to do. Yes, definitely not. And so that's just the statics part of pressure or fluids. So I have to have a fluid or I have to have a gas in order to have a pressure, because measurable. And that gets us through chapter 11, and there's 3 more to go, and we're just going to touch on parts of it. Okay. Yep. All right. I thank you for watching.